Hi everybody. Today we're gonna be talking about compaction of soil, what the compaction is, why, and when the soil needs to be compacted. It is an important topic which is also related to soil improvement as well.
Compaction is the method of packing soil particles by mechanical means to lessen the air content in soil and therefore increasing the soil density. It is employed for road and earthen embankments where soils are needed to be compacted to their densest state. At this stage, the soil reveals the most suitable geotechnical properties. There are three main aims in the compaction of soil. The first one is to lessen voids and therefore the permeability of soil. The second aim is to raise the shear strength and thus the bearing capacity of soil. And the third aim is to make the soil less sensitive to volume changes and therefore the inclination to settlement under load or under the effect of vibration. The success of the compaction process depends on several factors. Among them are the nature and the type of soil, that is to say, sand or clay, uniformly or well graded, plastic or non plastic, etc. The moisture content of soil layer at the time of placing, the maximum possible state of compaction obtainable for the soil, the maximum amount of compaction reachable under field conditions, and finally, the type of compaction equipment being used. To determine compaction properties of soil, a series of standard Proctor compaction tests are run on soil specimens with various water content. In the test, the soil is compacted in a mold that has a volume of about 950 cubic centimeter, the diameter of which is around 100 millimeter. During the laboratory test, the mold is connected to a base plate at the bottom and to an extension part at the top as shown in the figure. The soil is mixed with different amounts of water and then compacted in three equal layers by means of a hammer that delivers 25 blows to each layer. The hammer has a mass of 2.5 kilograms falling freely from a height of 300 millimeter. The mass of the compacted soil is recorded at the end of each test, and the water content of the top and bottom part of the soil specimen is measured. When the dry density and corresponding water content are gathered for each test, the data are plotted as the water content against the dry density as shown in the figure here. The idea is to determine the maximum dry density and the optimum water content. In the figure, air content curve is also included. This is a theoretical curve and it is obtained from the equation given here. Now, this is an important criteria it tells you that all the compaction point should lie to the left of this curve. The maximum point of this curve tell us that the soil grains here are densely packed. Soil has a good strength and stiffness, and it has low permeability. Is there any difference between the compaction properties of coarse-grained and fine-grained soils? Yes, there is. The compaction curves of coarse-grained soils usually reveal more pronounced peaks with respect to fine-grained soils as shown in the figure. The green curve for sandy gravel and the yellow one is for highly plastic clay. Additionally, the dry densities of coarse-grained soils are higher than those of fine-grained ones. On the contrary, fine-grained soils demand more water for better compaction, and because of these, they usually have greater values of optimum moisture content, varying from 15 to 20% in comparison with coarse-grained soils whose optimum moisture contents range from 10 to 15%. Compaction of soil affects its structure as well. For example, if clay soil is compacted with a water content on the dry side of the optimum, as shown by point A in the figure. By the way, the left side of the compaction curve is named as dry side of the optimum, where soil has lower water content. And the right side of the compaction curve is named as wet side of the optimum, in which soil has higher water content. At point A, soil will have a flocculent structure because at low water content, the diffuse double layers of ions encircling the clay particles cannot be fully developed. For that reason, the interparticle repulsion is lessened. This lessened repulsion brings about a more random particle orientation as shown at point A in the figure and a lower dry unit weight. On the other hand, when the water is increased, in other words, when the water content is increased, as represented by point B in the figure, the diffuse double layers surrounding the particles increase, thus increasing the repulsion between the clay particles and results in a lower degree of flocculation and a higher dry unit weight. Continuous increase in water content from point B to point C widens the double layers more. This widening causes an ongoing increase of repulsive forces between particles, and therefore the degree of particle orientation becomes greater, and the structure of soil becomes more or less dispersed one. Nevertheless, the dry unit weight drops because the added water dilutes the concentration of soil solids. At a given water content, higher compactive effort gives rise to a more parallel orientation of clay particles, which in turn brings about a more dispersed structure. Particles are closer and soil has a higher density and lower water content as shown in the figure. Now, if we compare point B with point E, we can see clearly that compactive effort increases the dry density and lowers the moisture content needed for compaction. And this is clearly observed in the figure. The values of the maximum dry density and optimum moisture content are used to carry out a successful work in the field. The soil mass is compacted in layers, named as lifts. The lift thickness seldomly goes beyond 300 millimeter. As the coarse-grained soils are compacted in lifts between 250 millimeter and 300 millimeter, fine-grained soils are compacted in lifts ranging from 100 millimeter to 150 millimeter. There are different types of field compactors for these aims. Let us see what they are. Smooth wheel rollers are one of them. They are suitable for proof rolling subgrades and for finishing operation of fields with sandy and clay soils. These compactors provide 100% coverage under the wheels with contact pressures as high as 310 to 380 kilonewton per square meter. They are not appropriate for producing high unit weights of compaction when used on thicker layers. These equipments can effectively compact 2 or 300 millimeter thickness of layers. This is another type of compactor called pneumatic rubber-tied rollers. They are better in many respects than the smooth wheel rollers. These equipments are heavily loaded with several rows of tires. Tires are closely spaced 4 to 6 in a row. The contact pressure under the tires can vary from 600 to 700 kilonewton per square meter, and they can produce about 70 to 60% coverage. Pneumatic rollers can be employed for sandy and clay soil compaction, and the compaction is accomplished by a combination of pressure and kneading action. Another one is ship foot roller. They are drums with a large number of projections, as you see in the figure. These are called projections. The area of each projections may range from 25 to 85 centimeter squared. These equipments are most effective in compacting clay soils. The contact pressure under the projections can vary between 1,400 and 7,000 kilonewton per meter squared. In the course of compaction in the field, the initial passes compact the lower portion of a lift. Compaction at the top and middle of a lift is fulfilled at a later stage. Vibratory rollers are highly effective in compacting granular soils. Vibrators can be connected to smooth wheel, pneumatic rubber-tied or ship foot rollers to generate vibratory effects to the soil. The vibration is achieved by rotating of center weights. Handheld vibrating plates can be effectively used for the compaction of granular soils over a restricted areas. Vibrating plates are also gang mounted on machines, which can be used in less limited areas. For the compaction in field, soil is spread in layers and a prearranged amount of water is sprinkled on each layer of soil. Thereafter, compaction is launched by a selected roller. Some factors must be taken into account to accomplish the desired unit weight of compaction in the field. These factors involve the thickness of layer, the intensity of pressure applied by the compaction equipment, the area over which the pressure is applied. These factors are crucial because the pressure applied at the surface decreases with that, which brings about a decrease in the degree of soil compaction. In the course of compaction, the dry density of soil is also influenced by the number of roller passes. The dry density of a soil at a given moisture content increases up to a certain point with the number of roller passes. Beyond this point, it remains more or less constant. In most cases, about 10 to 15 roller passes produce the maximum dry density economically obtainable. It appears very difficult to compact soil to its maximum dry density in the field, especially regarding the procedures and equipment employed for this purpose. What is the quality control for such work? Yes, it's not always possible to compact soil to its maximum dry density. For that reason, an acceptable range of dry density is used to control the field compaction work. The working range of field water is 95% of maximum dry density on the dry side of optimum moisture content, and the same amount, which means 95% of dry density on the wet side of optimum. In this way, the lower and the upper limits are thus defined. It is important to note that compacted soil wet of optimum for expansive and collapsible soils, which are vulnerable to volume changes, and the soil dry of optimum for the granular soils, clay sand, and the sandy clays, which are less sensitive to volume changes. The standard steps to determine the field density of compaction include sand cone method, rubber balloon method, and nuclear density method. Since the sand cone method is very well known and widely used, a brief description of which will be given. A sand cone test is commonly conducted at the compaction site to determine the dry density and water content of compacted soil. To ensure a high level of compaction, it is necessary to perform at least one test per 1000 cubic meter of compacted soil. The sand pouring to the vise consists of a glass, steel or plastic cylinder and a metal cone connected to it as shown in the figure. Initially, the cylinder is filled with a sand, preferably uniformly graded sand with known density, and the weight of the sand cone apparatus with the cylinder filled with sand is determined. The weight of sand to fill the cone is also determined. A small hole about 100 millimeter in diameter and 150 millimeter in depth in the compacted area is dug out, and the weight of the excavated soil is determined. The water content of excavated soil is also determined. This can be done in the laboratory. And the sand cone apparatus is placed over the hole by means of a guiding metal plate, and the hole is filled with sand by opening the valve as shown here. The weight of the sand cone apparatus with the remaining sand in the jar after operation is also determined. Since we have all the quantities measured, we can calculate the unit weight of the soil as follows. The weight of sand to fill hole, volume of the hole, weight of dry soil, and finally the dry unit weight of the compacted soil. Now let us use the information we have learned so far for an engineering application. Shown in the figure as the standard Proctor test for a gravelly sand, which is to be used as a base course of a highway embankment. You are asked to specify the compaction criteria for the field, to suggest field compaction equipment that would attain the desired compaction, and finally, to define a suitable quality control test. Because the soil is gravelly sand, it is best to carry out compaction on the dry side of optimum water content. The first step is to determine the maximum dry unit weight and optimum water content. Since the Proctor test results are given as a compaction curve as seen in the figure, the maximum point of bell-shaped curve will give us the maximum dry unit weight and the corresponding optimum water content. They are 19.6 kilonewton per cubic meter and 5.8% respectively. Second step is to specify dry unit weight and water content for field compaction. Again, to determine these, we need to read the 95% of maximum dry density from the compaction curve. 95% of maximum dry density is marked on the compaction curve, and the corresponding moisture content or water content is obtained. So the 95% dry density is 18.62 kilonewton per cubic meter, and the corresponding water content is 4.3. The third step is to determine the field compaction method. Since the soil includes a larger portion of sand than gravel, a vibrating roller is the most suitable one. Finally, the final step is to specify quality control equipment. For these, either the sand cone or the nuclear density meter is convenient. Now, let us review what we have learned so far. I know you dislike taking quiz, but don't forget, it is another way of learning. The first question: compaction is the process of soil densification that takes place because of the what? You are talking through your head. The answer is not D. It is B. Expulsion of air. Second question: compaction works best for what type of soil? Be careful. Waiting for your reply. Come on. Yes, it is C. It is best for gravelly sand. Nice going. The next question: the highest level of compaction for clay can be typically attained by what type of equipment? Sorry, it's not true. The answer is B. Ship food roller. The fourth question is: the zero air void curve can be obtained. No idea? Okay then. The answer is C. It is a theoretical curve that cannot be achieved in practice. The fifth question: how many blows per layer are used in standard Proctor compaction tests? You should know this. It's an easy one. Yes, that's it. It is C, 25 blows. The next question: data from standard Proctor compaction tests are as follows. The maximum dry density of soil is 1.80 grams per cubic meter, and the optimum water content is 14%. What will be the minimum value of dry density that can still satisfy the quality control requirement in the field? This is easy as well, an easy question. Come on, you should do this. No, no. Who said that? Yes, it is. It is 1.71. How did you get it? 95% of maximum dry density. Well done. In standard compaction test, soil is compacted in, yes, the answer is C. It is compacted in 3 layers. Good job. Another question: expansive soils should be compacted. No idea? Come on. The answer is B, on the wet of optimum.
And the final question, increasing compactive effort in compaction brings about what? No, not only lower optimum moisture content, but also higher maximum dry density. So the answer is C. That's all. Okay, folks. Thank you for your attention. Have a nice day. I'll see you later.